Hi, everybody. I figured I would give you a little additional information on the final. Not so much that. I just want to kind of go over just to reiterate, because I'm not quite sure what was in that other presentation, because I did it a year or two ago. It doesn't really change. I starts with digestive phys. Understand that basically you're looking at the what the end product or the end point of all of this is digestion and absorption. So we have to look what to digest. You have to break it down to the smallest possible particles, and that's breaking it down. Whether it's a monomer carbohydrate, whether it is an amino acid, whether it is the constituents that make up fats, that are there, or the constituents that make up nucleotides. Basically, that's the responsibility of a variety of enzymes to take it down step by step until finally the final touches, so to speak, whether it's oligopeptides or oligosaccharides, then finally we're going to get it down by the brush border enzymes are going to control everything. Different things are absorbed in different areas. The vast majority of absorption occurs in the small intestine, but understand that there's a little bit that goes on in the large intestine. Mostly it's just kind of fine. It's why it's non essential because you can supplement for it. I mean, it finalizes the amount of water that it absorbs. The longer it's there, the more water absorbs, the shorter. That's the difference between constipation and diarrhea. But certain things, vitamin K, certain kinds of B vitamins, and things like that are typically finalized in the large intestine. There's a lot of chemical signals. It starts with the stomach with gastrin, and then gastrin along with histamine, sometimes acetylcholine, sometimes serotonin, all play a role in the activation. The gastrin, I think, is the linchpin for most of this and is there, and they stimulate activity. And again, once we get to the small intestine, what just to preface it, a lot of it is stretch receptors, osmoreceptors, and pH receptors. And then what goes on when it gets to the small intestine, you have basically cholecystokinin and secretin that both play a really pivotal role in liver and pancreatic activity. That's what they're all about. So you should know what enzymes do what and where they're produced. We know amylase. Mostly we have salivary amylase. We have it in the small intestine. So it starts with amylase and kind of ends with amylase when I think of it this way. Fats, lipases, we see in the stomach, we see in the mouth, so in a couple more places, and then eventually in the small intestine. And when we begin to see proteolytic enzymes, they don't start to the stomach. So the stomach and the small intestine play the greatest role associated with that. So we see a lot of those types of things that are there, and just look for where they are. The vast majority of the enzymes are either produced within the pancreas, the liver to a much lesser extent, where you're really just looking at the bile and the bile salts that are there. And then the isolated ones from the mouth being lingual lipase and salivary amylase, and the stomach, the start of proteolytic enzymes and a certain amount of gastric lipase. And other than that, it's pretty much between the small intestine and whatever the contribution the pancreas makes, particularly for the remaining amount of proteolytic enzymes that are there. So the big player is always, and the essential part is the small bowel. Basically, everything shakes there. It's pH adjusted. We go from acidity to alkalinity. All of the things that are we find in there. So there's a lot of things that occur in there. And so understand structurally, it's all about surface area. They come from those tiny fingers we call villi, and we come from the brush border, which of all the cells that surround each of those little nubs, villi called microvilli, and they create just an amazing amount of surface area proportionally that are there. Within each villi is the lacteal. That's the lymphatic structure surrounded by the capillary bed that plays such a pivotal role that are there. And so, of course, everything that makes its way in, basically from a secretion, unless it's produced there, has to find its principal way into the digestive tract, and that's really the common bile duct, okay, which is the combination of the pancreatic duct and the hepatic duct, hepatopancreatic ampulla and sphincter, whatever you want to call them, but that's what they are that are there. The roles of the appendix is something that's important. Exactly all the events that go there. Remember, the appendix is perhaps ancillary lymphatic, but more or less a storehouse of bacteria that helps to reseed the large bowel, particularly after bouts of colitis and diarrhea. And again, our reference point for these proteolytic enzymes, they're all in, we call collectively they're enzymes, and they're in the precursor stage, so they're the ogen stage, so we call them zymogens. So you have, whether it's trypsinogen or chymotrypsinogen, doesn't really matter what they are. They're all in that pepsinogen, they're all in that precursor stage, and they have to be activated in order to be in. But the reason that is true is once they're activated, they're indiscriminate. If it's a protein, they gobble it up. So they have to be held within a structure protected by mucus so you don't effectively auto-absorb, which is part of the tragedy when a bowel ruptures or someone has pancreatitis. When we begin to see leakage of these into the abdominal pelvic cavity, they're indiscriminate. They'll gobble up anything, and everything's made out of proteins, more or less, that are there. So understand that we have different things that are broken down, but just to reiterate, it's only the smallest, really functional unit that are where absorption occurs. As we make our way into the world of the kidney, understand it's functionally, it's all about this, effectively, what we refer to as the nephron. The nephron, and there's two of them. There's the juxtamedullary ones that are all about water concentration, and the cortical nephrons, which are much more about the, basically the electrolyte balance, absorption and secretion of all the various things that are within the filtrate. That's the key player. There's two components, principally when we get to the glomerulus itself, the filtration apparatus, and the capsule and its extensions, which are the tubules, collecting duct, etc. It's a very interesting blood supply because it's arterial to arterial, because it's a high pressure filter, and so we don't have to spend any energy in producing the filtrate. Filtration is a passive process in that regard. So we rely on basically what I like to say, what drives the bus. So most times concentration gradient. In this case, it's pressure that's driving the bus. And then see what happens. It spits out this filtrate, anatomically, it's collected in the Bowman's capsule, the stem of that effectively funnel system. That's all sorts of neat and twisted. That's the proximal convoluted tubule. You have either a long or short loop, then the distal convoluted tubule, and then finally, we wend our way into a series of collecting ducts. But the vast majority of what's happening is accomplished in the proximal convoluted tubule. The vast majority of the reabsorption and a lot of secretion. And a lot of times we reabsorb stuff to create gradients that we secrete later. That's an interesting part of the process as well. We even do in the short loop portions that are in the cortical nephrons, you're still doing some of that. A little bit of water, a little bit of electrolytes, as opposed to the long loops where you have that fascinating system of the countercurrent multiplier to basically concentrate the urine and extract the water, and then the exchange system, which is pulling out the electrolytes and exchanging them so it can keep the gradient in place. Multiple entries into the convoluted tubules, those long loops and tubules make up that wonderful pyramidal structure, that sort of membranous kind of linear structure that's there. And it's, to me, it's fascinating how it's all sort of tied together. That's there. The juxtaglomerular apparatus and the renin-angiotensin mechanism go hand in hand. I always misspell renin with two N's, and it's supposed to be one. It's just me. I give up. Okay. The components of it, the macula densa, which is different than the macula lutea, which is in the eye. The macula densa is a dense area with sensors, okay, that are all part of it and play a role with those granular cells and the mesangial cells in controlling the process. You'd be familiar with all of those. We resorb the vast majority of the filtrate, about 99%, okay. And so all of those are important. All the ways that the angiotensin works when it's released by the juxtaglomerular apparatus when the blood pressure is low, basically tensing the blood vessels. Name tells you exactly what it does. Thirst, antidiuretic hormone, provoking or evoking, maybe a better word, stimulating the production of aldosterone, and then aldosterone inserting within the distal convoluted tubules and the collecting ducts, those passageways for sodium, and where sodium goes, water is sure to follow. I'll do Mary Our Little Lamb once again. That's there. So all of those are part of it. It's all based on sympathetic nervous system because there's no parasympathetic innervation. We control blood pressure by controlling diameters of blood vessels. That's all about the sympathetic system. Okay, so that and really that's much of the basis of physiology. And just to review those things that are there, what drives the bus? Mostly it's active transport and then secondary active transport for secretion and for reabsorption. More passive movements we see associated with water movement and in some other areas that are associated with that countercurrent mechanism. And certainly, again, filtration by definition is a passive motion that's there. Don't forget about transport maximums. I made a big deal of those with regard to glucose and what they implicate. What you're not going to find in the urine, you're not going to find cells. If there's glomerular damage, you find cells and proteins. Those are signs of it. You find white blood cells. You find red cells. You find stuff that shouldn't be there because you know what should be there. And all of that is part of it. Know the basic chemistry behind what urine is. The fact that it's it's pH, it's hypoosmotic nature, etc., things like that. And then we look closely at the reproductive systems, both male and female. So effectively, it's 4 chapters because you have to think male and female repro are separated. So exactly what they are and what their roles are. So we know the testes make sperm and testosterone. Okay, the sperm in their form are basically immobile and immature. They mature and gather the ability to move as they become adult sperm for whatever they are, spermatozoa and spermatids, all that stuff. The meiotic stuff, which I don't ask any questions about, within the epididymis, which is just another long tubular structure, convoluted, and its exit point is the start of the vas or ductus deferens. Okay, don't forget about cryptorchism, the undescended testicle, and what the problems that are associated with it. Testicles descend because of the temperature gradient, as you know. We know that there's a unique barrier because sperm are produced post puberty, so therefore the self non-self issue becomes significant, and what that implies that are there. What's in the ejaculant itself? If you talk about number, it's sperm. If you talk about volume, it's fluid, and the fluids are effectively let me put it together for you. The fluids are seminal fluid, probably 2/3 to 70%, prostatic fluid, and then a little bit of the lubricant itself, and then the vast number of those teeny tiny sperm, hundreds of millions of those that are in roughly this half a teaspoon to a teaspoon of ejaculant that we find. What does the seminal fluid do? We realize there's a certain amount of nourishment, the basis of fructose for nourishment, some of the enzymatic activities that are there, the prostatic fluid, the white milky kind of appearance that it has, the fact that it plays a role in activation, etc. And how we determine when there's prostate problems. Remember the digital rectal exam, the role of the PSA. How we learned about this in autonomic, the relationship between stimulation and climax, if which part of the nervous system is responsible for which. That's important. The beg your pardon, the hormones that control the roles of GnRH and LH and FSH, and what they in turn produce, where they're located, where their production comes from, and what they do. So I think all those things kind of summarize that. The role of nitric oxide is something that we talked about. What's the makeup of testosterone and also estrogen and progesterone That's all important. We get into female reproductive. What are the what is we talk about some of the problems, a little bit on sexually transmitted diseases, so some background on pap smears and gonorrhea, and maybe a little bit on syphilis and ectopic pregnancies, and usually the big problems associated with what we collectively call PID, or pelvic inflammatory disease, which means that the infection has ascended past the uterine area, and now we're into the tubes and the ovaries and those that broad ligament areas that are there, which are sort of intertwined. So they all become inflamed, and what that means: ectopic pregnancies, early onset of early need for hysterectomies that are there, ovarian dysfunction, infertility, however you want to describe it, that are there. The role of the basalis and the functionalis with regard to the uterus, the role the spiral arteries play with regard to all of those things, where the breast plays into it. And the nature of the breast tissue, remember, anatomically is mostly fatty tissue. The glandular structure, the importance with regard to the lymphatics and what they significantly mean. Okay. uh, and the fact that the drainage of the breast and into the lymphatic areas, and why we look at it so closely vis-a-vis breast cancer, which is such a problem. The roles of progesterone and estrogen, where their major points of activity are. Estrogen is all over the system. Progesterone is much more, involved in menopausal and uterine function, perhaps more so than anything else. And certainly everything playing a role, all of those agents playing a role in masculinization or feminization, depending on whether it's a man or a woman, whether the events that occur with menopause, I think they're important. What we know about follicles, okay, another name for the mature or formed follicle, you might remember it's called the Graafian follicle. The different cycles to know very well whether we're talking about the ovarian cycle and the menstrual cycle. What are the events? When do they start? What's the one that has the finite amount of time associated with it? What hormones are active in each? Remember that table I love to go over. That's part of it. Where fertilization occurs, the role of the corpus luteum, what is the corpus albicans, etc., etc. And these are really the kinds of things that I covered. And there's, as I always end it with, like a bunch of true falses, which I've already covered. And I think that this basically is what I wanted to talk about. So just a little heads up on some stuff that I think you're going to find important. It didn't take terribly long to do this. I just thought I'd give it to you. And uh, if I don't get a chance to speak to you and you are listening to this, I want to tell you how much I enjoyed working with you for this term. And thanks for everything. It was really a privilege. Uh, and it always is for me to interact with wonderful, engaging, and even occasionally enthusiastic students. Thank you. Goodbye, and have fun storming the castle.